Hi there and welcome everybody. My name is Ashley Crane and I'm the Sales Manager at Quantum Design UK and Ireland. I have the pleasure of joining you today along with my colleague Stefan Kaiser, who is a Sales Manager at InfraTec. As is quite usual, we normally get a number of people join us just in the early minutes of the presentation. So I'd ask you, those of you on the line, just to be patient for a minute and we'll very soon get started. Excellent. So we've just had a few more people join the webinar, and I'll just say again, my name is Ashley Crane, and I'm the Sales Manager at Quantum Design UK and Ireland. And today we'll be talking with Stefan Kaiser, who is the Sales Manager at InfraTec. The purpose of the webinar is that there are 1,001 applications for thermographic cameras with individual requirements that might include speed, dynamic range, resolution, remote triggering, etc. And today we will be presenting InfraTec's range of cameras with a focus on how to select the right camera and options for your particular application. So first of all, thanks everyone for joining us. I do hope everyone is continuing to stay safe and well in these challenging times. I'd like to thank Stefan for joining us with his technical expertise, and also Emily and Angela at QD for helping to organise this webinar. We've estimated about 45 minutes for the webinar, with a structure that I will first make a short introduction to quantum design, and my colleague Stefan will then take over to discuss how to identify the cameras and options to suit your applications. And then towards the end, we should have sufficient time for any questions. The way that we would like to do this, please, is should you have a question during the presentation, please write it in the question panel in the GoToWebinar software, and we will go through each of the questions in order at the end. So we're about ready to get started. We don't anticipate that there will be any technical hitches, but if any should occur, please bear with us, and if necessary, we will attempt to restart the webinar. So to begin, I hope everyone can see my screen, and I will now give a brief introduction to quantum design. The local UK office is located in Leatherhead, which is in the southwest outskirts of London. In the UK, we have a specialised group of people in sales, marketing and service, and we are part of a global organisation with a presence in 20 European countries, multiple offices throughout Asia and North America, and with our ultimate parent company being Quantum Design International in San Diego, USA. We are a hybrid manufacturer and distributor, which came about by the merger of two companies, the first being Quantum Design, a North American manufacturer of low temperature instruments for the measurement of magnetic and physical properties, and the other company was LOT or LOT Oriel, a well-established distributor of scientific instrumentation throughout Europe. We've been in business for 35 plus years and therefore have a lot of highly experienced and knowledgeable colleagues on hand to help you with your work. This is a slide illustrating our global structure and explaining where the UK office sits within our European organisation and alongside our offices throughout Asia and the Americas. Alternatively, you can see we have a presence across the continents and all around the globe. Focusing on Europe, you can now see a map of our presence across many European territories through a combination of offices, distributors and partnerships. As mentioned, as well as being a distributor, we are a manufacturer of equipment for the measurement and characterization of fundamental properties of materials at low temperature or high magnetic fields. Two of our flagship products are the MPMS, which is a squid-based vibrating sample magnetometer, and the PPMS, which is more suited to investigating bulk properties such as heat capacity, electron thermal transport, and other optical or magnetic properties. Also, some more universal products that we manufacture in San Diego. Our most recent systems include a range of helium liquefiers for the recovery or recycling of helium. And our newest product is the optical, which is an ultra-low vibration 1.7 Kelvin, 7 Tesla magneto-optic cryostat designed for microscopy experiments. Then we come on to our more broad portfolio of products that we distribute. As you can see, we cover many different applications with an offering of various cryostats, imaging cameras from X-ray through IR, even hyperspectral cameras, some fairly niche products such as spectroscopic ellipsometers, a range of products in complementary areas such as electron and X-ray microscopy, as well as a variety of optical and photonic components. So this slide shows an overview of the partners we work with here in the UK and Ireland. Hopefully you'll be familiar with most of these, or at least some, but if not, please take a moment to browse through our webpage later after the webinar. As you can see, I've highlighted our partner InfraTec, who are a manufacturer of infrared cameras and thermography solutions headquartered in Dresden, Germany. And also, finally, I'd like to ensure that you know that in the current situation, it's still very easy for you to get hold of the quantum design team through video conferencing with our sales and service people and with our partners. We've been doing this pretty much for the last 6 months as a matter of course. It's worked very well, and it's via Microsoft Teams, which you do not have to have installed as long as you have access to a computer with audio or a webcam if you prefer. For anyone who has not used it yet, it's very simple, and we just send you an invitation link. But I think most people have been working like this now for some time. Should you have any questions after today's webinar, or if you prefer a dedicated one-to-one follow-up with a member of our team, please just let us know, and we'd be very happy to set this up for you. So just obviously usual details, our contact details, as well as our website, the address which you should see at the top of your screen. You can follow us on the social media platforms of Twitter and LinkedIn to ensure you're up to date with our latest releases and information. For more detailed information, we also provide a newsletter, which we send out quarterly to our subscribers. So please do let us know if you'd like to receive a copy of this direct to your inbox. And so that's my introduction complete. I have the great pleasure to hand over to my colleague Stefan Kaiser, who will explain the different features and options available from InfraTec to address your applications. Thank you. There you go, Stefan.
Yeah, very well. Thanks, Ashley, for the kind introduction. So hopefully all of you guys should see now my screen, and I will go on with my little presentation today, which should be the following: how to find the perfect camera for your application. And the topic should be on your and application. So that means we will focus on different aspects to find the perfect IR camera or thermographic system for you. So from my background, from my experience, I know that there are 1,001 applications, and none of these are really similar. So you have to know the principles, how to help a customer, what is necessary to choose the perfect camera to fulfill the measurement situation. So basically, this is really the aim. So it's different, for instance, if you do PCB board analysis, what is interesting for this kind of application, or what is necessary to monitor and to optimize 3D printing processes. Do you want to monitor the build of the part itself, or do you want to monitor the 3D printing machine, for instance? Sounds pretty much the same, 3D printing, but two different approaches of finding a product for the customers. And simply there are high-speed tasks like these airbag tests. You have different demands than the others in terms of speed, for instance, in terms of handling the machine, synchronizing them. And there are also special tasks like visualization of gases and different approaches like this fireball here. Just as a quick example of the variety of applications you can find an IR camera for. So this would be the topic for today. Short introduction about InfraTec, of course, and first that you know to whom you're talking with. Then some physical aspects about different sensor technologies, because they are crucial. For two different types of cameras, I will present some parameters mixed in with InfraTec product range, some examples of applications. So without further ado, quick introduction about InfraTec. So we are a German-based company, currently approximately 230 employees. InfraTec was founded in 1991 by our two management directors. So we grew up quite nicely over the last 30 years nearly. And we are focusing on two business units. One is the so-called infrared sensor department. Currently, we face challenging times because our sensors are built in the ventilators, highly requested these days. But I'm working for the infrared measurement division. So we are dealing with IR cameras, so two-dimensional arrays of infrared technology, and not only in single standalone systems, which are normally used for research and development, for non-destructive testing, for process control, predictive maintenance, a lot of different applications and fields. But we also are dealing with turnkey solutions. That means automated systems in the 24/7 approach for different kind of industries. And we mix these hardware components really well with services and knowledge all around thermographic systems, the IR in general. So this includes trainings, this includes services like measurement services, but also the software you need to run these systems are manufactured in-house at InfraTec. So we present a variety of different services to really give you a good user experience from what you're buying from InfraTec. So, and what is InfraTec is mainly famous or well known for is the high resolution IR segment. So we are proud to present the highest resolutions in the market, either for so-called uncooled cameras, but also cooled photon detectors. What these are, you will learn during the next minutes. But we are focusing on the high-end demands and the high resolution cameras. As I said, the hardware is only the half of the rent, so you always need a good quality software with all the functionalities, with the possibilities to control the cameras, to acquire the data, and that's why we decided to develop these also on our own here in Dresden, in our headquarters, so we are able to react on customer needs on our own camera development. So this is something to round up our offers, which are like the following. So we're not only offering hardware equipment like the camera bodies, like the lenses, but also you can expect the full package, ready to use one, also with PC hardware, with the full accessories package, with the software, but also with trainings. These days, of course, as online courses, we are ready to do this, and we all already doing this. So this is a fully welcome package for you to really get something you can start from the first second you get the products at your desk. So now I want to switch into the topic right now, how to find the perfect IR camera, and I want to start with this first assumption. So all of you have your specific application in mind. Either you have a laboratory, want to do some measurements, if you have a research project, or you have a specific task in the industry to optimize a product or something like this. And you already did a little bit of research that the tasks you want to do or you have to do are solvable in a way with IR technology. So mainly it's about contactless temperature measurement, and there are some basic fundamental physics in here. You check them and you came to conclude that a measurement device, an IR camera, will help you fulfilling your tasks. And now it's your topic to find the product fulfilling these tasks. And you will shortly notice in the market that there are a variety of products from little tiny swap devices, not larger than your thumb, to large cooled cameras. And from the first sight, you would maybe a little bit overwhelmed and not clear what to choose for your application. And that's why we are here to help you guide you through this decision. And first, I think this is also obvious that there are different segments of IR cameras you can find. So there are entry-level cameras for tasks like predictive maintenance in the industry, but they are also cameras who are really dedicated to R&D, high-end and professional systems for customers who have really high demands, who want to push the limits of their developments, and gaining basically knowledge about this processes they want to investigate. So materials testing, for instance, is an application for this. But also with these different segments came different price levels, of course. But I have to disappoint you at this point that we will not talk about the budget so much here. We really want to focus on the application, on things like the precision resolution, thermal resolution, as well as spatial resolution, but also about some aspects sometimes forgotten by the client. So how to integrate such a camera into your measurement facility, how to really handle such cameras. But first of all, it's important to understand, to repeat that we are talking about the thermal infrared here. So this is a spectrum beyond the visible. And the basic thing to understand, or the basic principle, is that the heat coming from an object is transferred into IR radiation, or other way around. Every object that has a higher temperature than the absolute minimum of 0 Kelvin will emit IR radiation. So this is the clear physical background how we can give you a temperature reading of the temperature by measuring the IR radiation in these bands beyond the visible. And this is a kind of overwhelming slide here, representing the Max Planck's law. But it's kind of helpful to get a first idea of what kind of system makes its starting point for you to choose an IR camera. So this slide simply shows you that, of course, the amount of IR radiation increases with the temperature. That shows these different lines here in the middle. But you will also see that this is not a constant curve, but these curves have a maximum in different wavelengths, which you have on the x-axis and the below. So you clearly see that it's more likely for a high temperature application to looking for a camera in the mid wave or in the short wave. But if you looking for cryo applications, then you see this little blue line here, and you notice that there's almost no radiation in the short wave or in the mid wave, but a lot of radiation, or the peak of radiation, is more in the long wave. So this overlaps, this overall charts overlaps with your experience. Maybe a red gluing piece of steel is visible with your eyes, that you know that it is hot, but you cannot distinguish steel in between 100 and 150 degree. You do not want to touch it, of course, if it is 150 degree, but then an IR camera helps you probably with this. The Max Planck law is a general law, so it's not the last piece of information you want to deal with, but it gives you a good idea where to start digging into the technology. In addition to this, you have to know that IR cameras are manufactured for the so-called atmospheric windows. So simply the air that surrounds us is not transparent for the IR radiation over all wavelength. So we have these typical IR windows which are in midwave. There's a present one here from 3 to 5, and the other one, the most likely one, is from 8 to 14 micrometer. You see that there we have a good transparency, and that's why the commercial available products for are sensitive in these windows. So you will hardly find any camera that is sensitive at 6 micrometer, for instance. Why this is important? Because we are not living in an optimal physical approach. So we're talking about real objects. That's why the IR radiation coming from these objects is not constant over the wavelengths. This is sometimes challenging, but sometimes you can use this for your advantage. So what you see here is the spectrum of glass as an example. And you see here these fundamental aspects. So the object can be transmittive for IR radiation. The object can reflect the IR radiation and can emit the radiation itself. And you see here, for instance, on the green curve, which is the emission of glass, around 8 micrometers, you have a really high emissivity. So that makes it highly likely to measure on glass. That means glass surface. But on the other hand, if you do not want to measure on the glass surface, but looking through the glass, you thinking about a wavelength more between 2 and 3 micrometer. And by choosing simply or thinking about these wavelengths of these spectra, you can choose your IR camera according to your tasks. And there are cameras also in the market that can be equipped with spectral filters that you can switch in between different sensitive ranges, say it in that way, that you can do things like the examples on the right, measuring such a light bomb on the glass and through the glass with the same kind of equipment. So this is sometimes possible, sometimes not. So some kind of approach, what is my material, what are my measurement optics made of, is also a good starting point to think about what kind of IR camera I need for my application. Referring to this, sometimes it's also necessary to look onto the optical path of your measurement. So especially in the R&D, there are sometimes processes that are located in a measurement chamber, simply from the conditions, from special gases or from temperatures or whatever, or you need to protect the other equipment from laser influences. And then you have to think about also how can I do these kind of viewports for my chamber. What materials are there? You find some examples here, but also they need to be IR transparent, but also they have to withstand your processes. So, for instance, germanium, you cannot heat this material over 100 degrees Celsius approximately to be useful for an IR viewport, or the mechanical stress you can put on germanium is not so high as well. So for high stress applications, it's more likely to use sapphire windows, for instance. But as you see, sapphire is more likely to be transparent in the midwave. So this also can be a limiting factor for choosing an IR camera, simply to make the measurements happen when you have an IR viewport in a measurement chamber, for instance. But as I said, we also wanted to speak about the general technical approach of IR cameras. So there are two different kind of IR detectors, and this is this is necessary to know to start the conversation regarding on speed, regarding on image quality, and regarding on available lenses. So you have to know that there are two kind of cameras. They are so-called cooled cameras. They are based on photon detectors. These are detectors that are they need to be cooled typically to 77 Kelvin, which is the temperature of an liquid oxide and nitrogen. And they are so-called thermal detectors or microbolometers. These detectors are not cooled simply because they have a different working principle. They work in a way that these pixels they adapt to the IR radiation in a way that they will change their temperature itself, and this temperature change will be converted into a change in resistance, electrical resistance, and you can then analyze this change in resistance and convert it to electrical signal, which is then corresponding to the IR radiation, giving you after the calibration and reading in DC or whatever. So this is important to understand, but more important is to have an idea about the outcome of these different technologies. So again, on the left-hand side, you have these cooled camera detectors, and they are available in different wavelengths, in the short wave, in the mid wave, and then the long wave, of course. They are available in really large FPA sizes, so more than HD is really possible, but they are also well known for being useful for high-speed acquisition. So these cameras working in the so-called snapshot acquisition mode. This is important. Snapshot means that you will read out all the pixels at the same time. So there's no time delay in between the individual pixels. On the other hand, we have these thermal detectors, these microbolometers detectors again. These are well known for the long wave infrared between 7 and 14 micrometer typically. They are also available in high resolution. So SXGA is the current top for really radiometric camera systems, but they have an disadvantage that they are working by the line-by-line acquisition mode. So that means each line will be read out after the other. So from the bottom to the top, you have a time gap in between, and they are simply reacting not so fast as these kind of cool detectors. So to give you an example, what does this mean, not so fast? Imagine you have an object like this, simply object moving from the left to the right, and you monitor this with an Uncooled detector. Then you will get for each pixel and sharp image of this object moving from the left to the side. But if you monitor the same object with a microbolometer detector camera, you will see a smearing over the detector, so the shape will be distorted, looking like this, and this makes it often hardly possible to measure any meaningful temperature information if the relative movement in the scene is too quickly. As an understandable example, this is something I did in my office. Quite an easy example. So imagine you have two cameras looking at this little ball here, and I let this ball free fall from my hand, and I captured the images after approximately 50 centimeters free fall. So it's easy to understand that the ball then have a little bit of speed, but not too fast. But the result in these images are shown in these little clips here. On the left-hand side, you will have the snapshot photon detector, and you will see for each individual frame, I have sharp edges. You can see the heat distribution on the ball coming from my hand quite nicely over all frames. And on the other hand, you will see the microbolometer detector, and you will notice a clear motion blur when you see this image here. And only on the bouncing back on the top of this amplitude, you see that the ball relatively stands still, and you can do good measurements then. But when the ball has its speed, then it's hardly possible to see any good results with a microbolometer detector. Another example for this is this application we had with a client. They wanted to monitor these parts from a train. Basically, you have here the wheels and all the elements around the wheel. And we did a simple test with them. The train simply moved along its path, and on the left-hand side you have the snapshot detector with 200 hertz. Everything is clear. You can see really the objects and the details. And on the other hand, you have this line-by-line microbolometer with 60 hertz acquisition speed, but you clearly see the motion blur and you can hardly see anything. So thinking about the speed of your process is really essential with choosing an IR camera and what detector technology you need. But it's not only about the geometrical movement, maybe for instance, but it's also about the speed of your thermal event at all. So if you have, for instance, in electronics, something that heats up quite quickly but cools down quite quickly, for instance, tiny little resistors on the chip level or whatever. So these time constants of these little objects are really quick. So they heat up quite fast and they cool down quite fast. And you need to have a detector that is able to follow this process also. And there the microbolometer detector has another draw, which is simply that these pixels, as I said, they need to follow the IR radiation because they will change their temperature itself. So typically for each pixel, this needs approximately 10 milliseconds for one pixel to change its temperature due to a temperature change in your scene. So this is then also a limiting factor if you have thermally fast changing processes. You simply cannot resolve it with these kind of microbolometer detectors. But of course, on the other hand, we have these kind of cooled detectors, these snapshot detectors, and these detectors, they have an settable, more or less settable integration time here in the microsecond range and not in the millisecond range. So we can really capture fast processes, not only geometrical, but also thermal. And you will be able to set these integration times in respect to the temperature ranges you want to see. And here you see two examples of a rotating object with different integration times, and you see the effect of what is basically, this is the same frame rate but with different integration times, and you see simply you can adapt these kind of technologies onto your application. And an example here is from the materials testing. This is widely done for the development of new materials, or this is basic research. What you see here is a sample that will be squeezed and pushed in a cyclic way. So mechanical stress analysis investigated with a photon detector of ours. And typically in these experiments, a crack will form through the part. And at the top of this crack, you will have a thermal event that is located in front of the crack. And often you can see this thermal events in the sample before a crack is forming. And this is the video here you will see in this image, that this pulsation of the force you stress the object will result in a pulsation of a thermal event in the part. And simply because you have the amplitude of your of your force such high with around 100 hertz here, you simply need a camera that can follow this process and is sensitive enough to give you readings like on the right hand side to follow these kind of processes. And for this kind of stuff, you need a high-speed cooled camera. But overall, also in respect of the different kind of products or the segments I spoke earlier, you will notice that there are entry-level cameras, but also high-end and professional cameras. They will also differentiate in their overall image quality. What you will see here are examples for the so-called NATD, which is or represents the signal-to-noise ratio somehow. And you will see, or you can expect, of course, for a low-end camera, for a low budget, that the thermal sensitivity will not be as high, so you simply cannot resolve temperature changes so nicely because the noise is overlapping your signal. And for high-end and professional cameras, you can expect better quality sensors, simply with better image quality. You can compare this with your smartphone without a flash, trying to capture images in the dark. So simply there's less radiation, and you cannot you clearly see differences in sensor quality by trying to do this. But unfortunately, for temperature measurement, you cannot use flashes, of course. Another aspect, of course, of choosing an IR camera is the field of view and also the instantaneous field of view. So this is sometimes a battle in between the object size and the detail size. I recommend to really focus on the details you want to measure. For instance, at this PCB board, what is the smallest detail you want to see? This is the starting point of choosing a camera and the lens, because these parameters are influenced by the lens, but also by the detector. You can switch from this kind of standard scale here to the microscopic scale, what's really necessary if you think about micrometers of elements, for instance, in PCB boards or chip level in the electronics. But of course, there are also applications in which you need telephoto lenses for power line inspection, for instance, ground-based power line inspections for surveillance applications. And then you think about field of views in the meters range, IFOV in the centimeters range. And this slide maybe gives you an idea of the likelihood of which camera you choose for different field of view demands. But you have to keep in mind this rule of thumb here, that the resolvable detail, which I labeled here with X, corresponds to the IFOV in your application. So it's simply that you cover one detail, for instance, a resistor on a PCB board. You should at least cover this with 3 pixels. That 1 pixel is simply laying 100% on the object, giving you a good reading. It would be even better to have 5 pixels on a detail to even resolve your detail a little bit better. Sometimes 3 pixels is a little bit less. So as a result, I mentioned here this example of a switch cabinet. So on the left-hand side and on the right-hand side, you see the same switch cabinet but monitored with different resolutions. And on the left-hand side, you see maybe it's clear that it is a switch cabinet, and you see some hotspots. The question is if they are really hotspots. And the camera in this example gives you a maximum reading here of this element in the middle of 61.3 degrees. But when you monitor the same scene with a high resolution camera, you will notice not only that you can resolve more details and it's more pleasant to your eye, but you also notice that the maximum reading now is not 60 but 80 degrees. This can make a real difference for your application is it only a warning that this element is simply under stress, under workload, and simply the temperature is normal, or this element is under too much stress, or it's likely to have a fault because it's too hot. So often the resolution and also the IFOV and the spatial resolution is critical to applications and really to get the nice readings you want to have. So that's why I recommend to start with the IFOV first, and then thinking about the field of view afterwards, if you can cover a scene with one shot or you have to do multiple shots or so. To give you a perspective of the current market regarding field of view and available lenses. So these microbolometer cameras, you can expect to have it from an easy microscopic lens to telephoto lens, approximately 15 micrometers or 17 micrometers actually to 120 millimeters in focal length, something in between. But the variety of lenses available and resolvable details is for photodetector more wide. So there we have microscopic lenses as well as real telephoto lenses. So the flexibility of photodetectors is larger, and they are more likely to be used for different applications, not only by their speed but also by their ability to resolve details or to provide different kind of lenses. As an example, let me show you this kind of example here again in electronics maybe. May you're familiar with this kind of product here, with this kind of touch sensor at the bottom. And we figured out that this cover of this touch sensor is IR transparent. So without deconstructing the iPhone, we are simply able to look through this cap and visualize the fingerprint sensor of an iPhone. It's just visualization because the detector is only active when you have the thumb on the sensor, but simply you cannot look through your thumb. So it's an example of available optical performance here. And when we look this sensor with an MX1 lens, you will have this appearance with a pixel size of 10 micrometer approximately. When you zoom in to a certain region, you have this left-hand image here, but when you add a lens with a magnification of 8, you can clearly see here the details on the chip level, and this is a good example of what is the detail size you can expect from these cameras nowadays. But of course, there are other applications requiring handheld usage. For instance, if you think about predictive maintenance, then you have to think about handheld movement, having a camera with a battery, a camera with a monitor, but you have to be aware of your limitations of your camera then. So it's likely that these handheld cameras are microbolometer cameras, and then you should know that you have limits in monitoring fast-moving objects, for instance, or you cannot expect to have a flexible camera, handheld camera with a microscope, for instance. But there are clear applications requiring a handheld camera, and we also able to provide these handheld cameras, of course. Coming back to spectral thermography with these filters, there are different applications requiring the use of spectral filters to looking on specific also absorption bands of different materials. I already mentioned the example with the glass, but this can also be done with different gases for flame analysis or for flame visualization, for instance. And there are cameras in which you simply install such an filter to monitor different wavelengths. But our cameras are equipped with so-called filter wheels, in which you can put in multiple spectral filters. And of course, these are motorized, so that means you can fully remote control your camera and choose in between seconds, in between different spectral filters, and then add variety to your experiments. You can instantly change between on flame and through flame and monitor more or less the same scene with two spectral ranges. This you should consider for different applications. But it's not only simply the camera and the speed and the IFOV. Sometimes it's also relevant to think about your overall measurement approach. So for instance, do you have access to your camera all the time? Do you have changing conditions, for instance, in the field of depth in electronics? Or have you have installation and a protective housing? So I really recommend you to consider your demands from these aspects of your measurement situation too. So for instance, if you have demands like this, in which you do not have access to your camera, in which you have limited field of depth, then you should, for instance, consider a camera with a motorized focus, because then you simply can have all the controls remotely from a PC. For instance, you can fully control a camera and fulfill your tasks, not having the demand of having one focus and then doing an experiment and then change the focus and doing the experiment again. So this can add flexibility and usability for your products as well. When we speak about usability, then of course we speak also about interfaces these days. So at InfraTec, we rely on standard interfaces like GigE or 10GigE, providing a good availability in the market, but also good performance, but also long cable lengths, for instance, flexible cables. And what you see here is an interface plate of one of our cooled cameras. And one aspect, of course, of these cameras is also to trigger them, for instance, for fast moving objects, you want to trigger them, or with laser applications. Laser illumination, for instance, is a application in which you want to precisely trigger your camera, and then the performance of such triggering is also part of the discussion of what kind of camera you need to choose and what kind of signals, of course, TTL and something like this. So this also can be an aspect of choosing an IR camera interfaces and triggering and IB timestamps and stuff like this. So now it's my honor to present you a little bit the InfraTec product range. I want to start with the so-called VarioCam HD series. These are microbolometer cameras. So they are located also in the high-end segment of these technology. So what you can expect are high-resolution cameras from InfraTec, as I said earlier, but also with this approach of having or addressing the higher segments, you can also expect a good thermal resolution, a good measurement accuracy. So we providing really top-end products here. Only to sum up the models here, some of the key figures, of course, very robust products with an IP54 rating, with broad measurement ranges exceeding up to 2000 degree if necessary, fully radiometric lenses, of course, interchangeable. The example here is a handheld camera, but of course these cameras are also available as stationary cameras with the same functionality, with the same functionality, that means with the same measurement performance, the same detectors, the same resolution, the same thermal resolution, but of course a stationary camera is 100% remote control. So these cameras include a motorized focus from stock. But the benefit of a stationary camera can be an even higher IP rating, which is beneficial for different applications. The variety of lenses is also quite high. This is just an overview reaching from a wide-angle lens over to standard lenses with close-up lenses to telephoto lenses. Of course, these are interchangeable. So these cameras are likely to be flexible for the higher demands for microperimeters, and you can equip different lenses to modify a little bit the field of view for different applications. But of course, this is our own development based on photon detectors. The series is called Image IR. So these cameras are developed by ourselves. We produce them here in Dresden. We calibrate them here in Dresden. So we have our own calibration lab. And we distribute them worldwide in the UK by the help of quantum design, thankfully. And we are doing this kind of stuff over 25 years now. So we have a lot of experience based on the needs of our customers. And this very camera series is really based on a flexible approach. So the camera is based on different modules that can be combined for different detectors, to spectral filters for different ranges, to motorized focus options, really to different kind of interfacing, GigE, 10 GigE, but also advanced trigger interfaces, for instance, with different analog inputs as well as also as digital inputs. So these cameras are not only providing the performance of a cooled detector, that means high speed and good and superior image quality, but also add a ton of flexibility to be modified to your application and also to be future proven, because some of these aspects, like the front module, can be updated in the future. If your application changes, then we can upgrade these kind of cameras by this modular approach. So here's an overview of these of the models here. There's the typical performance features. So you see the variety is a little bit wider than for the VioCam series. So there are models like the Image IR 5300 that are really focused on the absolute high-speed acquisition up to 100 kilohertz in the subframe, but we also have the current top model, the Image IR 10300, which is currently the largest resolution you can get on the commercial market currently. But there are also cameras like our working horse series, the Image IR 7300 and 8300 models. This camera is the most flexible camera from ours, with a decent amount of resolution, with a decent amount of speed, but also with the advanced features we developed for these cameras, like high sense calibration, which enables a ton of flexibility with unique features like microscan and HDR. And there are really new developments in the market, stuff that no other manufacturer can really provide, like our Image IR 9400, which is, I call it a 2-in-1 camera, because it can provide a really large FBA resolution with 1280 by 1024 pixels, but also can be switched into a binning mode instantly, and then provides you a high-speed resolution, high-speed imaging of up to 600 hertz. So this is really a product adds a ton of flexibility and highly used for researchers who have different kind of applications and want to use the cameras for different applications simply. So the next slide simply show you a summary of all the features we provide for these cameras. Again, high resolution is the aspect we are focusing as a company, but also do not neglect the needs of high-speed acquisition of precision of thermal sensitivity here. And we cover currently mainly the mid-wave and the long wave, but there's also a new model approaching, which is a shortwave camera from this image IR series. So they are here. You can see other unique features to our image IR cameras. As I said, advanced triggering as a feature, having multiple filter wheels for spectral imaging is a unique feature. We're really pushing or putting a lot of work into our calibrations. So for instance, the cameras will be calibrated 3 times. So it means that one calibration at room temperature, one calibration at lower temperatures, and one calibrated at higher temperatures. So camera temperatures. So we put these cameras into chambers in which we heat up their environmental conditions, so that you as a customer can expect a stable calibrations even if the camera temperature changes due to change in the environmental conditions. And we rely on, as a roundup, on 10 gig E, for instance, as a source of interface, which is high speed and provides a ton of advantages like long cable lengths and stuff like this. As a roundup, you will see here the wide range of lenses, some examples of the field of view. So this is something I do not want to speak to you in detail. You can find a field of view calculator on our website and play around, and it clearly can see the difference between different resolutions and different lenses and stuff. In the next slides, I will go through some of the unique features of InfraTec because I have the feeling that we run out of time a little bit. So InfraTec developed a so-called microscan feature, which boosts the resolution of such a cooled detector. And you can see here the difference between the native resolution, which is VGA, and then with microscanning, which is an optomechanical technique, you can instantly boost the resolution and quadruple the amount of pixels. And this is really helpful for edging out your existing detector. And this technology is in this way advantageous that, of course, VGA detector is simply cheaper than a standard SHGA detector. But adding microscan, you can mimic the performance of an SHGA detector, but simply you do not have to spend so much money. So this is a kind of cost-effective way to boost resolution as well. Another aspect which is quite nice for our latest development, the image IR 9400, is the so-called binning feature. So that means that we bin 2x2 pixels together on a hardware base. And this leads to an increase in thermal sensitivity, but also the achievable frame rate. And the boost in frame rate is even higher than what you do when you use such a detector in a subframe. So this is something really edging out the detector again. And it looks like this. So the standard detector is 1280 pixels by 1024 pixels again, with a 10 micrometer pitch. And what we do on a hot wire, we bin these 2 pixels together, form virtual new pixels, then with 640 by 512. But as a result, we gain thermal sensitivity and pure speed. And as an example, you see here the soldering tool and letting simply a water drop fall, and you simply can see the evaporation of the water drop, but also when the water drop falls again, this little sparks. So this is simply a nice high-speed imaging. And the beauty of this technology is really that you can switch instantly in between these 2 modes. In 1 second you have a high-res camera, and in the other second you have a high-speed camera. So if one of you searching for the flexible camera for different approaches, I highly recommend to have a look at the Image IR 9400. But also a good, nice development of InfraTec is so-called high dynamic range for Image IR that provides high or wide temperature ranges, which is normally an issue for cooled cameras. And the example here is a light bulb, a little bit old-fashioned, but it indicates the performance. In the video, you see the light bulb is turned on and quickly changes its temperature. But our camera with HDR is able to follow this process quite nicely over a wide range of temperature. So here you see the turning on effect and the cool down again. And it's really a high dynamic process we can mimic or we can follow with our Image IR series with HDR. So a summary of what I tried to present you today is there are two major technologies in the market, so-called cooled detector cameras represented by our Image IR series. They are famous, or they're well suitable for high dynamic processes, fast changing processes. They are likely to choose when you have the demands of the best spatial resolution, for instance, in a micrometer scale, when you have demands on the best thermal resolution you want to have, the best image quality, when you have demands on precise triggering, and if you have demands on spectrothermography, then these are bullet points for you to consider a cooled camera more likely than Image IR from InfraTec. But on the other hand, there are the microbolometer cameras represented by the Viocam series. These are suitable for, in brackets, ordinary processes with a low dynamics, slow changing processes with a moderate spatial resolution, with low demands and triggering, but also if you have mobile applications. And fortunately, these cameras are more cheaper than cooled detectors. They are more likely for maintenance-free applications, so implementation into industrial products, processes, for instance. And then it's more likely that you choose a Viocam, of course, by the help of Quantum Design, Ashley, and me. We are welcome you to get in touch with us. Speaking about your application, it would be a pleasure if you think about your application a little bit through, about physical properties of your measurement objects, maybe about the temperature range and temperature dynamics, about your objects and detail size, get an idea about the necessary lens maybe, and then we will help you to choose the perfect product for you. And this should end my presentation here, a little bit over time, to invite you to really get in touch with us, start a conversation, and then we will help you also, again, respecting your budget, of course, finding the right product, added with some training that you have a good user experience fulfilling your task at the end. So thanks for your attention. And Ashley, would you be so kind and then read us through the questions, and maybe I will answer them directly with the help of my slides.
Sure, absolutely. So thank you very much, Stefan, and thank you again all for your attention. We're going to take a minute now to give you the opportunity to enter your questions into the question box, please. So do that now. And then we'll run through them in order in just a few seconds. Also, I'm going to very quickly put a poll on the screen, which will ask whether or not you'd like us to get in touch with you. And it's just a simple one-click yes or no if you have a specific application that you'd like to discuss with us. So I'll leave that there just for a moment. And as I say, hopefully you can still enter your questions into the chat box, and then we can have a chat about your specifics. So one question, Stefan, was in the beginning you have shown a measurement of a gas bubble temperature. Is this possible for pure air, or do you need to have a specific gas for the measurement?
As you seen at the beginning, I showed the slide of these atmospheric windows, and that we use these atmospheric windows to have our detectors located in which the air has a high transparency. So that answers the question that surely for these kind of visualizations of gases, you should have a gas there, CO2 or whatever, simply because you're measuring on the absorption band of these gases. So for your pure air, it's not possible because you want to look through it for most of the tasks. But for specific gases, you should do a little bit of a research maybe for your gases if it is something specific about the absorption bands, and then we will find maybe a suitable spectral filter to modify the camera for this approach. So it's simply for specific gases.
Okay, excellent. Thank you, Stefan. We have a related question as well, which is to do with the material transparency for monitoring processes inside machines. I know this is something that's come up in discussion between yourself and I, which is whether or not glass windows are sufficient depending on the temperature that's being measured. Could you comment on the type of transparent materials that are useful when using temperature measurements?
So maybe I go back into my slides.
Just give me a second. I think I need to close the poll in order for you to be sharing your screen. Let me just check. So
yeah, I will share my screen again. So
there we are. Thank you.
So the answer maybe to this question is, as I said, the typical product to have in a handheld camera, for instance, is a microbolometer detector. And what you will experience when you stand right in front of your office window with a microbolometer camera, with a handheld camera, then you will see yourself reflected in this kind of glass surface, simply because, for instance, you see here a high amount of reflectivity in the sensitive range of such a microbolometer detector. So unfortunately for a lot of the customer cases, glass is not sufficient as an IR window. Simply you have to choose or think about materials that are IR transparent in the sensitive range of your camera. So these here are examples of IR transparent materials. Some of them are used for IR lenses as well, for instance, germanium or sapphire. And you have to think about the combination of the transparency of your window and the spectral range of your camera, in combination of what is happening in your measurement chamber again. So if there's a lot of mechanical stress on your window, you maybe choose sapphire again, because it can handle a lot of mechanical work as well. And another aspect can be barium fluoride as a material, but it's toxic. So sometimes it's not likely that it is used for viewports as well. So hopefully this answers the question. So ordinary glass, but again, you really have to look at the glass type itself. So that the spectrum I have here is for nothing special. So it really depends on what material you have in your existing measurement chamber or viewport or whatever, and you have to maybe ask the manufacturer to give you a spectrum, and then look for a good transparency in the IR wavelength band in general, and then you can choose your IR camera from this.
Excellent, thank you. And just one more moment, if anybody does have any questions that have been raised again, please enter them into the question box. So far we've covered the two that were asked. We'll have a few moments. Okay, sorry. So that one has just popped in. Make sure that I'm actually seeing all of these. 1 second.
So maybe Ashley, I help you because the last question here I will answer directly about the magnetic fields. So
yes.
this is
Can I?
very special.
I'll just read the question, Stefan, for the rest of the audience. Sorry. So the
Okay,
question
cool.
is, what is the experience of the camera when this is installed in an environment with fluctuating electromagnetic fields? For example, if the electromagnetic field is 200 microteslas, perhaps this does not affect the IR measurement, but could affect the camera circuits due to induced currents.
Yeah. So this is exactly the question here. So what I only can give you from my experience, without knowing the exact numbers, but once I was at a customer who repairs electric motors, so kind of bulky stuff for cranes and stuff. So a motor half a square meter in diameter, and they had the problem that their existing IR camera produces faults by going near to these kind of motors. And I used an Biochem model for this client, and simply because it seems to be that the aluminium or the aluminium housing of our Biochem series protects the internal electronics from being disturbed by this. But we haven't tested these kind of cameras exactly to 200 microtesla or so. So maybe we need to give it a try, or if it's possible to use a telephoto lens to have simply more distance between the magnetic field and the camera itself. But also the housing of the image IR is made of metal, so can have good projection to some level. So it's a really specific question I cannot answer fully, because I do not know simply what 200 microtesla will have an influence, or what 150 Tesla will have an influence. So maybe we have to simply test this. Okay.
Thank you, Stefan. We can follow up offline, perhaps. I apologize, ladies and gentlemen. I've just realized that some of the questions were hidden from me, and I've now found them. So we will go through them from the start. So one question that came in was, may I know which model is suitable for furnace or boiler tube applications, and why?
This is a question, if I understand this correctly. So a furnace or a boiler depends on the material you're measuring, also the surface material of your objects. So it tends to be metal surfaces. Metal surfaces in general are complicated for IR cameras in general, because the emissivity of such an object over a wide range of the spectrum is poor. So the reflectance is dominating. So this is an issue you have to overcome first. And the other thing is, if you overcome this, then we are back in the discussion of temperature range, dynamics, and stuff like this. So this is maybe a question we have to discuss afterwards in detail with whom asked the question. So please come back to us directly, and we can have a chat about the process itself and all the details. And then so it can be both, maybe depends really on the details.
Thank you, Stefan. And so we have another question, which is, can you give an idea of how long it requires to capture a microscan image?
Yeah, of course, I can give you a perspective of a microscan. This is something not really detailed described here in my presentation, but it would you can imagine it as an active influencing of the beam inside such a camera. So normally the beam runs through, so the IR radiation beam runs through the lens and hits the detector in a quite straight way. But what we do is we influence this beam length, that we shift such an image by half of a pixel, so by a sub-pixel range, and this slightly shifts the orientation of the image on the detector. And when you do this 4 times in a row, you can somehow scan the image, scan the scene, and by then merging these 4 images together, you have a resulting image that shows you, because of the slightly different orientation, shows you details you normally cannot see, and boost the resolution by this. And there are different approaches of the merging of these images. So one approach is to reduce the frame rate and then only to look on the resulting image. One approach is to have some kind of a rolling image acquisition. That means once a time you only actualize the fourth, not the fourth, a quarter of all the pixels in an image. So you keep you displaying all of these sub images in the larger matrix. So this is maybe hard to explain simply by words. So, but it's basically scanning the scene by influencing the beam. That's why I talked about an optomechanical approach. So it is also available for stationary cameras of InfraTec. So, but of course, of this explanation, it's understandable that you may have you have an influence of this process on the dynamics on the speed. So there's a time gap in between the first and then the fourth image. Hopefully this was understandable for the attendee who asked this.
We can follow up if there's additional questions, of course. On that subject, sorry, with that attendee. We have another question, which is, could you please suggest which model might be useful for SPV active thermography?
So an SPV, I'm not so familiar with the abbreviation of this. But to give the other attendees a little bit of an idea, active thermography is highly used for non-destructive testing or for electronics also. And the approach is that you actively put some energy into the parts, electrical energy, light energy, or whatever. And by this active excitation, you can see other thermal effects than with passive thermography. And in the process of active thermography based on a synchronization, let's say in that way, of the camera and its excitation, and repeating this in a number of circles. So for instance, for electronics, you put in an alternating current into your part, maybe for 100 amplitudes or so. And during these 100 amplitudes, you are collecting images as a sequence. And as a result of this current, one fault or one defect or one tiny resistor will heat up and cool down, and again and again and again. And because you're measuring a sequence, you can apply a fast Fourier algorithm on this, and then simply magnify changes in these images. So this really edges out the performance of such a camera. So these little temperature changes caused by the current normally is not visible with passive thermography, simply because these temperature changes are too little. But with the consequence of the fast Fourier analysis, you can highlight these elements. Active thermography therefore can be done with a microbolometer as well as with an photon detector, but it's more likely to be done with a photon detector because you can synchronize these detectors better. The base performance is better in terms of thermal sensitivity, but also for the microseconds and the shorter integration times and the snapshot behavior. So there's actual footage available showing the differences on the same part between a photon detector and a microbolometer, and you can clearly see the differences. So I'm sorry for not knowing what SPV stands for, but it's more likely to use a photon detector, so in image IR for active thermography.
Thank you, Stefan. So we have two more questions. I'll go with the last one first, and the reason for that is because we've been asked for contact details. So I wondered if you could put up the contact details from the last page of your presentation, in case anybody needs to
sorry, at this presentation I do not have all this combined contact information, so I simply have mine here.
Oh, that's good. That's fine, because of course we'll pick up anything that we need to. And then the penultimate question, if you like, was what is the difference in the detector material used in plus or minus 2% measurement accuracies compared to plus or minus 0.5% accuracies?
So this is not so easy to answer a question because it's from my point of view not related really to the detector material. So there are different materials used for different kind of detectors. So if you go back to the slide in which we have these differences here, actually you can find photon detector cameras which have an accuracy of ±1, and you can find thermal detectors which have an accuracy of ±1. And in these days, you also find data sheets with ±0.5 or 0.3, but these are only valid for limited temperature ranges and for specific environmental conditions. So these 0.5 and 0.3, they clearly coming from these related body temperature measurements these days, and they are only suitable for limited temperature range and limited ranges for environmental or camera temperatures. To describe the whole calibration process of such a camera, it's a little bit more complex, but simply you have to understand the whole calibration process to really understand this. But for measurement situations in, for instance, in industry or in R&D, we're talking about wide ranges of temperatures, not so sharp and limited ranges, and then the top end of the current performance for both again is ±1% or ±1 Kelvin. So it's more likely that a cooled camera or so an MCT or an InSP will provide a more crisp image, but this does not fully relate to the measurement accuracy you have on a data sheet, for instance. And one last aspect maybe to this, when you think about measurement accuracy, then you always have to consider your physical properties of your materials you want to measure. So to say this in drastic words. It makes no sense to have the best the best camera in the world if simply the emissivity value of your part is not good, and reflective radiation is dominating in your scene. Then this will simply overpowers the performance of your camera and makes all the efforts on the camera and the calibration process of this camera useless, because the measurement, the whole measurement chain, if you want to say it in that way, will overpower this simply. So the crucial point in contactless temperature measurement is the emissivity of your parts itself. You have to consider this first, then thinking about absolute measurement accuracy.
Excellent. So, okay, thank you, Stefan. So I think we should be back now to the contact details. Stefan, is that correct? Is that what you can see?
Yeah, that's totally correct.
Excellent, good. So that wraps up all of the questions that we've received today. So obviously contact details are now displayed on the screen. I'm sure you have them, but please do take them down. Take a moment to contact us should you have any further questions. And I'd like to thank you all again for your attendance, and yeah, look forward to speaking to you about your applications in future. Thank you, Stefan, as well, for giving the presentation. It was very informative.
And, thanks everyone for joining, and also Ashley, thank you for organization and helping me with these aspects today.
No problem at all. Okay, I'll be stopping the broadcast now. If anybody has or wants to get a copy of the webinar, please let us know, and it will be made available. Okay, thanks everyone again, and bye-bye.